So good morning to you all. My name is Jan Verhagen and I will tell you why, to my opinion and personal experience, thermoset composites did not succeed in transportation equipment. I will try to explain from my point of view the barriers of commercial success for this and why I believe that with the new technologies and materials available in thermoplastic composites, this can be a success story. So my basic assumptions are very clear. Avoid black metal composites, I come back to that later. Think in commodity products, and commodity transportation equipment means high serial production, because one-of-a-kind production in composite material makes no sense, it's too expensive. The solution requires always new materials and new production technology, and I experienced that over the last 30 years, that every 5 years you have to renew the complete ideas about the structures. Reduced weight of transportation equipment, up to now, to my experience, never led or was an argument to pay more for this equipment. Now, with the current pressure of the carbon footprint reduction, this may be a new issue. So think in fibers. All over 4,000 years, the wooden trailer was developed and became a marvel of technology. This is another subject to talk about the Conestoga wagon. But in World War I, so many wooden trailers were destroyed, and due to the need of trailers, the shift to metal trailers was made very quickly. And in the interbellum, this technology of wooden trailers, which is a composite trailer, was completely lost. The metal trailer still has its place for heavy transportation equipment and all these things. But as from '68, the first aluminium trailers were built by Benalux in France. And this was because the aluminium extrusion technology was available, giving a lot of design liberty. In 1980, Fruhof, and I found this article back, Fruhof started with trailers where sandwich panels were used. Now, in the US, this is called a composite trailer because it's a composition of different materials. In my opinion, a composite trailer is something totally different. It is a combination of fibers and a matrix all over the structure. So in the 90s, early 2000, a lot of projects came up, and I call them failed examples, and this is not a negative mentioning, but these were trailers built by universities and consortia, heavily subsidized by the European community, by national subvention programs. But what they did is they made a working prototype, got a prize, an innovation award, and an applause. But since it was not designed for serial production, it stopped with one prototype. So as you'll see, there's a lot of examples. And one prototype, for example, this trailer, was in carbon fiber epoxy and costed 200,000 euro if they had to make a second one. So that is not sellable. I cannot imagine a transportation company who would pay that amount of money. So on the demand of customers of mine who were looking for lighter material for transportation of bulk and, for example, wood transportation, we started looking for building a trailer that was possible to make afterwards in a serial production. So I bought the scrapyard of Big Art Composites, the scrap of pultruded profiles, Big Art Composites, who is now Excel in Belgium, and we glued all these profiles together to the first trailer. And this was immediately a success, and the video of that trailer went around the world in '96. So we built 2 more prototypes for transport of bulk, and they drove each of them 250,000 kilometers without any problems. And what was important, these trailers had everything in it to be built in a serial production. So I attracted interested investors for that, and we started Composite Trailer, and we built 40 trailers in serial production. And most of these trailers were ordered before even the production started. So this was a real commercial success in the beginning. I will tell you later on that this was in the curve of the innovation, the early believers. We built them in Europe, and we had a license agreement with Mark Marietta in North Carolina, who built also the American version that you see here in the US. That we believed so strongly in the project, and a lot of people believed in it, is mentioned in the article in Reinforced Plastics, where Amanda Jacob described the whole project and the belief in it to be a commercial success in the future. It's a very interesting article to see how in 2006 we looked to the market of composite trailers. So we encountered a lot of barriers of commercial success. I go quickly over this because I will explain them in detail afterwards. We had an incremental reaction of the aluminum industry. The glue connection, the joining connection in serial production was always a problem. It is extremely difficult to integrate auxiliary parts that are common used in the market. The repair capabilities are very limited. We have the chasm of the market. I go very deep into that, and we have a limited capability to create an attractive design, a sexy trailer. So thermoset composite proved a lack of flexibility, and that was our biggest problem. And so immediately when we started, we got a very high reaction of the aluminum market. Nearly on every show I presented my trailer, they had a booth of aluminum, showing that aluminum could be much better engineered for trailers than they did at that time. They even published a book distributed to all the trailer builders about how to better engineer a trailer. So if you compare the benchmark in 2000 and the benchmark in 2004, 2005, you can see that the aluminum industry changed enormously their structures, improving, reducing weight, reducing the cost, and I was not able to answer with composite trailer for that because I had my serial production in start, and with thermoset composites there was no reaction possibility, even if we saw some improvements to make. The complexity in joining, what we discovered is that you practically need a quality controller next to every gluer, because for example in this connection of a floor and a sidewall, if you have the connection profile, which is a protruded profile, that is for example not cleaned enough in this area, well, under the pressure of the bulk it will break, and the repair capability of such a thing is enormously difficult. The auxiliary parts that are available, for example hatches, are made to be welded on a steel or aluminum structure, not to be glued on a composite structure. So you have to find new ways to connecting them, and that is costly and adding weight. So if we sold a trailer here in Lokeren, Belgium, which is the middle of Belgium, but the transport company went to Austria, which is 1,500 kilometers away, and got an accident due to rough handling of a forklift or something like that, there was no possibility to go over there and repair. So the transport company, this is rough handling, drove back 1,500 kilometers loaded, mostly damaging more the structure than we would have wanted. So you need very specialized repair shops. So the new concepts should take that in mind, that the impact capabilities of the material should be much, much higher than what we lived through with thermoset composites. So the classic model of the chasm of innovation is known. It was first published by Geoffrey Moore in early 2000. And when we made our business plan, we took this in account. This is the profit and loss curve. We took this in account. We knew there was going to be a chasm. That is that the pragmatists are looking very carefully to the visionaries and early believers and enthusiastic people. How will the trailer behave after 1 million kilometers? But for the changing material of the trailers, this was another problem. So if you look to the chasm, with our project, this chasm was, this gap was enormously big. So the barriers that we encountered are mentioned here again, and this is a very long period. The longer this period takes, the sharper the curve will be for going up in the pragmatists. If it is long enough, you will never take it up, and that's what we lived through. What was the reason? We couldn't react to all these barriers because of thermoset composites. It was too expensive to do, and I will show it to you later how this was. So let me give you two icon quotes. Brand Goldsworthy, who is called the father of composites and pultrusion, after I gave my presentation on the ice in 2002, we had a meeting and he said, "My friend, your project is wonderful, but it will only be successful once you use thermoplastic composites." So I was very excited, called home, I said I have a new technology, but in the evening Clem called me, who worked then for Goldsworthy, and he said, "Jan, slow down, 2 feet on the ground, this technology is far from being ready," and he was right. So when I heard the presentation of Robert Bryant from NASA on CFK Valley Convention at Airbus in Stade, I thought that the technology they are going to use was perfectly applicable with other materials, but with the same technology on the ground in transportation equipment. So I was very happy to meet that man. What we did is we selected materials and technology available. So we went to polyamide 6 organosheets where all materials will be built, and we tried to use technology available in aerospace in other environments. So we will adapt it. So if you think of a workshop, a thermoset workshop, where, for example, the wings of a wind turbine are made, or a boat, or bridges, is completely different from a thermoplastic environment. Thermoplastic environment, think of a metal shop and change the material to a thermoplastic shop. It's more in that direction that we have to think. So when we position Agasia, when I take the 0 point, the glass polypropylene environment, and then everything that is aerospace, don't look to the scale because I couldn't put that high enough, it would disappear from the screen. With my former technology, we were a glass vinyl ester constructions, and we think with PA6 that we can improve the performance at the same cost. But then we got in contact with Jones Manville for the new product, and what we see is that we even can higher the performance and lower the cost by using this kind of organosheet. And let me explain it a little bit further. When we thought of using polyamide 6, there was a lot of people having objections against that, for using that in transportation equipment, and we made a specification for this organosheet, and guess what? The organosheet of Jones Manville answers completely to our requirements. Everybody knows organosheets made out of multiple layers of unidirectional material. Jones Manville starts with a layup glass with a special sizing of their glass, and that means that the engineer can use much more or has much more liberty in using different kinds of layups. So we can use continuous woven fabric, non-crimp, and chopped roving, and also define the fiber directions already in the weaving, for example. So let me explain a little bit the GM organosheet that we use, and we believe in it. Is a standard glass fiber is bonded with an activator group. Jones Manville changed the grafting form, and it grafted with polyamide 6. So if you do the in situ polymerization of caprolactam with the fibers, you have as a result a very covalent bonding, a very high covalent bonding between the matrix and the fibers. So remember that I talked to you about impact resistance that we need. If you have the non-reactive glass with an impact and the same impact of a reactive glass, You can see that you here have a failure at the fiber matrix, and here you have a failure in the matrix, which is much, much better. And we did a lot of tests with impact, and they are very, very good. So the multi-layer organosheet that you can see here always has a problem of voids, which you do not have if you use a complete fiber structure and then insert the caprolactam. You don't have these voids, which is also a big improvement. So I just show you the composite engineering principles that I developed over these 30 years. I will not go in detail over it, but what is important that it led always to very costly tools, no flexibility after design, so redesigning with thermoset composites is not so easy. The Achilles heel is glue, always a problem, and in aerospace they overcome it with millions of rivets, which we didn't do in our trailers because of the cost. And auxiliary parts connections need interfaces, so this is something we could never overcome with the better engineering. So if we do the same engineering with thermoplastic composites, we do not need the costly tooling. We have increased flexibility of design and redesign, which is incredibly important. Welding and forming, connections for auxiliary systems, and what is very important, aesthetic design. Not only build something that is user-like, but also look-alike, and if possible, look better. Everybody in engineering prototypes knows these circles of prototyping. So from CAE design to material and refined material and part tests, you come to the building of the first prototype, with in mind that this first prototype is also a first of series. For in case of success, you do your production. You have the tooling, I put it in red because it's a barrier, you cannot go back. Then if you have afterwards, suppose you made, like we did, 40 trailers on the road, and you need adjustments on your design, you can only go back here. Otherwise, if you do this circle again, it's enormously costly. Because of your tooling, because of, for example, pultrusion equipment, is enormously costly. So if you go to prototyping cycle with thermoplastic material, this means that after first series, you can go back up here, do the whole circle, make your adjustments in your tooling, and build a better prototype or a better series material. So the company we started up early this year is called Agesia, and the final mission is that we will reduce the carbon footprint in total. I'm also Vice President of the European Composites Industry Association, UCI. We work very hard in the frame of recycling thermoset composites. We have the EcoTool, which works perfectly. But what I'm doing here with thermoplastic material is going up front, using other materials that is better recyclable, and it will never replace, for the moment, the thermoset in big series for wind turbines and boats and all this stuff. But in the place that we are doing, you can easily scrap the thermoplastic material and use it in a second level component. So we value long-term relationships where we will work together with companies that are interested in building prototype up to serial production equipment. We strongly believe in a co-creation where the end user or the end producer of the material is very narrowly involved in the design and development of the products. So we develop our structures components based on panels and on beams. And I can tell you that regarding the panels, we have developed a very strong thermoplastic sandwich panel. So, food for thought. We believe that doing what we do will facilitate the acceptance of thermoplastic composites and new technologies in aerospace, because we are not tied up with the TRLs that are absolutely necessary in aerospace, but that we can skip in transportation equipment. And I thank you for your attention.